block of mass m slides up a rough incline that makes an angle theta with the horizontal. The block is launched with an initial speed of v0, and the coefficient of kinetic friction between the block and the incline is mu k. Assuming the block remains in contact with the incline until it comes to rest, derive a symbolic expression for the distance d it travels up the incline before stopping. So let's start by possibly using Newton's laws on this problem. So here is a drawing of what the situation looks like. Here we have the incline and the block. I've represented it as a dot. And let's assume that v0 points in this direction, so it started by going up the incline like so. And so maybe we can use Newton's laws to find an expression for the acceleration of this block, and then perhaps we could use the kinematic equations to relate the velocities, accelerations, and distances, and we can probably use the kinematic equations to solve for the distance d. So let's start with Newton's second law, and let's draw a free body diagram of all the forces acting on the block. So I'm going to define the positive y-axis to be this way, and the positive x-axis to be this way. And so once we have established that, we have the normal force acting this way, normal to the surface, since it's in contact with the incline. We have the force of gravity acting downwards. And since the block is moving up the incline, the force of kinetic friction will be pointing down the incline, since it always opposes the relative motion between of the block with respect to the incline. So Newton's second law generally says that the net force acting on an object is equal to its mass times acceleration. And both the forces, the sum of forces and acceleration, are vector quantities. So we can decompose this F into x components and y components. And let's start with the y components. So in the positive y direction that we define, we have the normal force. And we also have the force of gravity, which is not really pointing along either the y or the x direction. So instead, let's decompose it. So I'm going to redraw this incline, and I'm going to draw just gravity for clarity. And this is the angle theta. And so we can decompose gravity into components in the x direction parallel to the incline, and components in the y direction perpendicular to the incline. And this is supposed to represent, this is a 90-degree angle here. So this angle is 90 minus theta. So that means this angle is just theta. And using trigonometry, we can find that the x component is just mg sine theta, and the y component is mg cosine theta. So we can add this y component to our force in the y forces, where we're summing all of the forces in the y direction. And this component in the y direction of gravity is pointing in the negative y direction. So we have minus mg cosine of theta. And that's all the forces acting in the y direction. So we can set this equal to the mass times the acceleration in the y direction. Since the block does not accelerate perpendicular to the incline, this is just 0. And we can simplify this to say that the normal force is equal to mg cosine theta. Now let's do it in the x direction. So in the x direction, we have the frictional force, which is negative, as well as the component of gravity in the x direction, which is also negative. And this is equal to the mass times the acceleration in the x direction. And one more thing, the magnitude of the force of friction the force of kinetic friction specifically is given by mu k times n, where n we found earlier, so we can substitute that in, and we get that the magnitude of the force of kinetic friction is just mu k times mg cosine of theta, where we plugged in n here. So with that, we can simplify it to say that negative, I'm going to pull out this negative sign, negative mu k mg cosine of theta, and this will be a plus since we pulled out the negative, plus mg sine theta equals m times acceleration in the x direction. And now we want to solve for this acceleration so that we can use it in the kinematic equations later. So all of these m's cancel out. So we get that the acceleration in the x direction is equal to the negative, and let's pull this g out too. Negative g times mu k cosine of theta plus sine theta. Okay, so now we have an expression for the acceleration, and this is in the x direction. So I'm gonna erase everything here. And we can move on to the second step, which is actually using the kinematic equations. So I'm going to drop the subscript since the acceleration in the y direction is 0. So let me just copy this here. And then okay, so now if you recall from our kinematic equations with constant acceleration, we have that the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration a times the distance d. And this equation is important to note that it assumes that the acceleration is constant, and from this derived expression, we know that all of these, g is a constant, mu k is a constant, and the angle theta is also a constant. Like, it doesn't change as the block moves. And that's why we can use Newton's laws to find the acceleration and then use the kinematic equations. It's because the acceleration is constant. If this incline were, like, say, curved, then we couldn't use Newton's laws, and we might have to use, like, something more general, like energy conservation instead, where the work done by friction dissipates the total mechanical energy of the block. So we have that the final velocity, it will be 0, since it starts with some initial velocity, reaches the tip d, and then turns around. So we want to find the maximum displacement or distance d, which is when Vf equals 0. So we can rearrange, and we want to find what d is. So let's solve for d. So d is equal to negative v0 squared over 2a. And our acceleration a is actually in the negative direction, so these will end up canceling out. So if we plug in a here, I'm going to plug it up here. Negative v0 squared over 2 is negative g times mu k times cosine theta plus sine theta. And so these negative signs cancel out. And then we can just simplify this to get that d equals v0 squared over 2g times mu k cosine theta plus sine theta. And so this would be our final answer. And so now there are actually a couple of things that you can do to like check whether this answer is feasible, because it's probably likely that you have not seen this specific answer before, or maybe you haven't seen some related answer style of this. So I'm going to put this final answer aside for now. I'm going to rewrite it over here. And then, so now that we have our answer, we can actually, there are a couple ways to like sort of check to see if it meets some sort of like common sense conditions. So one, we can start by doing something called dimensional analysis. So what this means is we are solving for the distance d, and the units of d are meters or some other equivalent length unit. So since d is equal to this whole expression here, this whole expression must also have the units of meters. Let's say that we're using meters in this case. So we want to check if the units of this side are equal to the units of this side. So the units of the left side are just meters, since it's a distance d. Now we want to figure out if the units of the right side are equivalent. So let's just plug in our units here. So v naught is a velocity, which means it has units of meter per second, and it's squared. And then in the bottom, 2 is dimensionless, this is 2. G has units of meter per second squared. It's like acceleration. Mu k is a dimensionless number. The coefficient of friction is dimensionless. Cosine of theta is a number, and sine of theta is also a number. So our only units in the bottom are meters per second squared. So if we simplify this, notice that the second squared cancel out, and we get meters. So that's our first common sense check, that the units on both sides are equivalent. And if they're not equivalent, then that means that we've definitely done something wrong, and we know for sure that our answer is not wrong. And if the dimensions are equal, it doesn't guarantee that your answer is correct, but at least you know it's not going to be way off. So the other thing that we can do is we can also check limiting cases. So maybe specifically we can see what happens if like theta is 0 degrees. In that case, you just have a block sliding on a flat surface, and it has an initial velocity v naught, and we want to figure out what the distance it takes to stop it is. Or take theta equals 90 degrees. And in this case, the block is just being shot upwards, and it's not really contacting the incline anymore. So the force of kinetic friction doesn't really act on it anymore, since there's no normal force perpendicular to it. And so in these special cases, the motion simplifies, and it's much easier to check if your answer actually aligns with your intuition. So let's start by maybe calculating what d would be for this scenario here, where we assume that theta is 0 degrees and it's just traveling in a straight line. So when theta equals 0, the only force acting on the block in the horizontal direction is the force of kinetic friction. And of course we have the normal force here and mg. And from the balance of forces in the y direction, N equals mg, and the force of kinetic friction is just mu kn, which is mu kmg. And so our acceleration, since the force of kinetic friction is the only force acting on it, our acceleration is just fk over m, which is just mu kg. And if you remember from the kinematic equation earlier, we had that v naught squared was equal to like negative 2ad, and then we solve for d. And this acceleration is negative since we chose this direction to be the positive x direction. The friction opposes its motion. So this a is actually negative, and the negative sign eventually cancels out. So I'll just drop it here for speed. But we can just plug this in. And so this is our result for when theta equals 0. And you can already see it's much simpler to derive. And this is something that you may have seen in a standard like physics course, where you might have derived this result before. So I'm going to write this down. So that's one case where we know what should be going on. And we can do the same thing for theta equals 90 degrees. So in this case, the only force acting opposite to its velocity is just g. So the acceleration is just g. And if we plug this back into our equation earlier, we just have that a equals g. And this is theoretically what we should get in this scenario. So now let's actually check if our result holds in these two limiting cases. So if we take the limit as the angle theta approaches 0 of this d here, oops, I wrote theta by accident. It should be 0 degrees. So as cosine of theta, when theta approaches 0, cosine of theta approaches 1, but sine of theta approaches 0. So this part cancels out, and we get v naught squared over 2g mu k cosine of theta. And cosine of theta is just 1 as theta approaches 0, so we can just drop this part. And this part exactly matches what we expected for this case. So that's a good sign. And let's do this again for the 90 degree case. For the 90 degree case, sine of theta is 1 and cosine of theta is 0. So this part disappears and we just get v naught squared over 2g. And this also matches what we would expect when theta is equal to 90 degrees. So both limiting cases turn out to be what we expect, which tells us that our answer is more likely to be correct. And of course, if one of these limits were way off, like maybe you would get like sort of a infinite distance or something, then you know that your answer is wrong, and you should go back and try to figure out what you did wrong. And of course, if we check, notice that mu k is in the denominator, so increasing mu k will decrease the distance traveled, and that's also what we would expect. So based on all these answers, or these checks, it seems that this answer does seem like a pretty plausible one. And so this is something that you should do if you have extra time after solving a problem. You can apply these checks to see if you're definitely wrong and need to go back and do something to like redo the problem. And that is how you would solve this problem here.